So in this video, I'm just going to run through a few straightforward questions on relative atomic mass. So this first one is about the definition, and then the next couple of questions we're going to look through some calculation-based questions that you would typically find in an exam. So I've chosen questions that are straightforward to begin with, and then have a few little tricks. There's always different ways examiners like to ask these questions. So we'll jump straight into it. If you're lucky, you will get a question like this. So nice and straightforward definition. Explain what is meant by relative atomic mass of an element. So key things to note here, there's normally 2 marks on offer for this, and all you need to do is essentially put down something along the lines of it is the weighted mean mass of an atom. So weighted mean mass of atom, that typically gets you 1 mark. Okay, that's the first marking point. And the second marking point will be when compared to a 12th the mass, forgive my handwriting, of carbon 12. That says carbon 12. Okay, and that's your second point. So weighted mean mass of an atom compared with the 12th the mass of carbon 12. Nice and straightforward. I'm not going to dwell too much on that. So moving on then to a straightforward calculation. So again, if you're fortunate, there will be a straightforward calculation like this. This is from a past paper. So sample of silicon, they give you 3 isotopes of silicon, 28, 29, and 30, and they give you the relative abundances of the silicon. So we've got 92.23, 4.68, and 3.06. So easiest way to tackle this question. Okay, now I will obviously do it differently to some people, how you've been taught it. They're all the same method. It just depends on which way you structure it. The way I always do it is essentially to find out the relative atomic mass. You essentially need to do 92.23% of 28, 4.68% of 29, and 3.06% of 30, and add them all together. Now, how you do this is entirely up to you. I typically avoid the division by 100. I think it makes things more confusing. So I tend to just stick with doing the base percentages. So I'm just going to work out 92.23% of 28 in the sum. So to do that, it's nice and straightforward. So 0.9223 multiplied by 28 is 92.23% of 28. You add that to the second value, which is going to be 0.0468 for 4.68% times 29. And then you're going to add that to 0.0306 times 30. And that will give you your relative atomic mass. Now, again, you don't have to do it this way. You can do 92.23 times 28, 4.68 times 29, and 3.06 times 30, and then divide everything by 100 at the end. It doesn't really matter which way you do it. Okay, as long as you're confident in a method, I say stick to it. Once you've got something that works, don't go changing it on my account. So if you have your specific way of doing it, as long as it works, go for it. If you do all of those sums, you end up with a calculator value of 28.0996. And if we obviously make sure we read the question, bit of exam technique there, 2 decimal places. So therefore it will need to be 28 point, and because it's at 99 or 996, you're going to need to go up to 10. Okay, so, and that's fine to do. That extra 0 is fine because you're rounding up 09 to 10. So that makes perfect sense. And that is 2 decimal places. Okay, it doesn't mention anything about significant figures here. Even if it did, that would still be fine. Make sure you put the 0 in. It's very easily forgotten. It's deliberately done to see if you'll remember to put the 0 on. Because when you round it, you go, oh, it's just 28.1. I'll leave it like that. No, put the 0 on. It's a second decimal place. Right. Bit of a harder question then. So it's the same idea. And when they ask these questions, you can't actually be asked anything different. Okay, it's always the same sort of mathematics, but they like to mix things up at A level. So this time, they are giving you the relative atomic mass of strontium. at 87.73, and they're telling you it consists of 82.9 of strontium-88, 6.9 of 87, and one other isotope. Now that's important. One other isotope means that the percentage of that isotope is whatever the remaining percentage is. So the first thing you need to do, really, is to do 100 minus 82.9 minus 6.9. That will tell you the percentage remaining. Okay, how much does your final isotope have as a percentage? So if I just put this in my calculator, I should probably do it in my head really, but I don't want to. You get 10.2. Okay, 10.2. So that's the percentage of your other isotope. And the rest is just basic mathematics, because we're going to do it in exactly the same way as before. Okay, so what we're going to do, same mathematics, same formula. So instead of doing it like we did last time, we're going to have an unknown in our equation. So this time we know what the result was going to be, but we don't know everything leading up to it. So let's put in what we do know. So we're going to do 82.9%, so 0.829 multiplied by 88. And we're going to add that to 0.069%, sorry, 6.9%, 0.069 of 87. Now, this is the bit that we don't know. Okay, so we know it's 10.2%, so I can put that in, 0.102. But we don't know what this is. So this is our x. We don't know what that is, but we know that the whole thing put together equals 87.73. So now it becomes a straightforward rearrangement exercise. So to make this easier, and whenever you see these big equations, everyone tries to do the maths and, you know, rearrange the equation. My advice is to keep it simple. Okay, there's a big section in the middle here. You can simplify massively. You can do this on a calculator. Okay, so put these numbers in, 0.829 multiplied by 88, and then add that to 0.069 times 87, and you get 78.955. So this whole thing equals 78.955. That simplifies things a lot, because we can now just simply subtract this 78.955 from the other side of our equation. So we'll do our little mathematics approach now, swap side, swap sign. And what we're left with is 0.102 times x equals 87.73 minus the total of that little sum there, 78.955. And you can obviously then simplify that little section. You can do 87.73 minus my answer, and you end up with, that is 8.775. And now it is a very, very straightforward rearrangement, because you've taken a difficult sum and done a simple rearrangement, simplified it down, and now all you have to do is to work out x. X is simply equal to 8.775 divided by 0.102. And if we do that, divide by 0.102, and we get 86.02. And that's our answer, and that must be our answer. So 86.02 is our answer, or 86, pretty much. But they don't actually specify what, well, actually, I suppose, not 0.2, it should be 0.3 if I round it. So they don't specify significant figures, so we'll just leave it there. The final question looks complicated again, but it's the same principle. Only thing this time is they're using very, very accurate percentages. So be careful of significant figures. I say this all the time, but no one ever listens to me. Significant figures are really important. You'll lose a mark immediately if you don't follow the rules. Again, the sample of magnesium, they tell you what the total relative atomic mass is, and they give you 2 isotopes, and they ask you to work out the third. The method is the same as before. Even though the numbers look a bit more, decimally, doesn't matter. Same principles as before. So 78.99 and 10 gives you 88.99, which means that the unknown is 11.01%. Okay, that's the one we don't know. That adds up to 100, and again, it tells you there's 3 isotopes in total, only 2 are shown, so the third one must be must be 11.01. Again, we're going to put the numbers in exactly as before. So 78.99 as a percentage is 0.7899 multiplied by 23.985. Just be careful with the transcriptions. It's very easy to copy a number wrong. And then you do 0.1 times 24.986. And then you add that to 0.1101 times x, which we don't know, and that equals 24.305. Again, same principle as last time. We're going to simplify the bit that we can work out. So those first two brackets, we can simplify very, very quickly. Okay, so if I add the first bracket's worth 18.94, if I add that to the second bracket, we can work out very, very quickly that we've got 21.44. So all of this is worth 21.444. I'm not going to write the whole thing out again because I think it's a bit counterintuitive to keep writing it out and over and over again. But what I will do is write the upshot of this. So 1101 times x equals 24.305 minus 21.444, blah blah blah. There's a lot of calculator numbers there. Just keep everything on the calculator. I'll just do that on there now, minus the answer. You get 2.86. Okay, roughly 2.86. Again, keep the value on the calculator. I'm not going to write the whole thing out because it will take me ages. And then, once you've done that, it's just a matter of rearranging again. So divide by 0.1101. So x equals that number divided by 0.1101. So let's do that now, 1101. Oops. And we get 25.982, etc. So it equals on the calculator 25.9822752. It says 5 significant figures referring back to the top. Therefore, to 5 significant figures, 25 is 2 significant figures, and 982 will be your other 3. And there you go. So there's some questions on relative atomic mass. Hopefully those have made sense, and it just shows you how, even though they can change how they're asking the question, it doesn't actually make a difference to the method. The method is the same, it's just what the unknown is that you're looking for.